In this video, we're going to learn about the ideal gas law. So in the past, we've learned about Boyle's, Charles, and Gay-Lussac's laws, and they can combine to give us the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. And the combined gas law is meant to relate initial conditions of a gas to final conditions of a gas. If we change the temperature, then what happens to pressure and volume, for example? But this is assuming a constant sample of gas, that we start off with a certain number of gas particles and we end up with the same. We're not changing that. Avogadro's law will explain to us the relationship between volume and moles of a gas. So this N is the number of moles of gas, and this V1 over N1 equals V2 over N2 is just a mathematical way of saying that the more gas you have, the bigger N is, the bigger its volume will be. As you add gas, the volume will increase. If you remove gas, the volume will decrease. And Avogadro's law is useful in getting us to what's called the ideal gas law, which does not relate initial conditions to final conditions of a gas given some change in temperature, pressure, and or volume. This will just tell us properties of a gas at some constant state, which does require the number of moles. So if we look at it, PV equals nRT. A lot of these are things that you already know. N, again, is the number of moles. What is different is the number, is the R. You've never seen R before. That is called the gas constant. And the gas constant is simply there to relate the units. If we have a sample of gas, let's say that we're trying to calculate the number of moles. We know the temperature is 100 degrees Kelvin, the volume is 1 liter, and the pressure is 1 atmosphere. We could calculate a value for N. That would be very different if we were to say that the pressure is 760 millimeters of mercury. 760 is very different from 1, and yet 1 atmosphere is 760 millimeters of mercury. So that's why we have R. It's simply to make it so that the units all work out, so that if I use 760 millimeters of mercury or 1 atmosphere, I still get to the same calculation for what N is. So our value of R and the units of R will change according to what the units are that I'm using. So if our units of volume are liters and our pressure is atmospheres, then this is the value, 0.08206 liters atmospheres per Kelvin mole. That will be our R. If we use liters and millimeters of mercury, or also known as torr, as in our measurements, then our numerical value of R will be quite different. It'll be 62.36 liters torrs per Kelvin mole. So let's try out a calculation. We have 1.00 moles of gas held at 1.00 atmospheres and 0.00 degrees Celsius. And we're trying to figure out the volume that the gas occupies. So we know that PV equals nRT is the equation that we'll use. We know that P equals 1.00 atmospheres, and V is our unknown. Our N is equal to 1.00 moles. Our R, well, we've got atmospheres, and it says what volume does the gas occupy. I suppose I could go with a lot of different things here. I'm just going to say we're going to solve this in liters. And so I'm just going to write a liters here. So, and I'll also say that it's question mark liters is our volume. So our R, we're going to need atmospheres for pressure and liters for volume. And when I go back here, I find liters and atmospheres per Kelvin mole. Our value of R is going to be 0.08206. So 0.082, was it? Yes, 8206 liters atmospheres per Kelvin mole. And our temperature is 0.00 degrees Celsius, which I need to convert to Kelvin, actually. I need to convert this to Kelvin. That is 273.15 Kelvin. And this does have the right number of significant figures because our conversion is a matter of addition, and the actual measurement in Celsius is precise to the hundredths column, and our answer here in Kelvin is precise also to the hundredths column. So if we put in our pressure of 1.00 atmospheres times, I'm just going to say V liters, that's equal to 1.00 moles. Sorry, this isn't writing very well. Times 0.08206 liters atmospheres over kelvins moles. Notice the moles and the moles cancel out. So PV equals NR, whoops, I don't need that. I'm going to be multiplying it by the temperature, which is 273.15 Kelvin. Our kelvins cancel out. And if I divide both sides by the 1.00 atmospheres, I will get V2, or sorry, V, not V2, I'll get V liters is equal to 22.4. So I encourage you to do the calculation yourself, but 22.4 liters. Now, I happen to know this. I didn't do the calculation in my head, but that 22.4, notice it has the right number of sig figs. There are 3, just like everything else here, except for the temperature and the R, which are more precise. Note this. 1 atmosphere, one mole at exactly standard temperature and pressure, standard temperature being 0 Celsius, standard pressure being 1 atmosphere. 1 mole of a gas at standard temperature and pressure will always occupy 22.4 liters, whether we're talking about hydrogen, oxygen, or any other gas. The molar volume of a gas will always be 22.4 liters at standard temperature and pressure. Hope this video has been helpful for you. Let me know your thoughts in the comments. Thank you.